phosphorylation for an immediate immune response. So there's an aspect to this that's actually normal within some of our cells, and specifically our immune system. So this is a fascinating article. And my recommendation, if you're going to pull one article from this presentation, I would recommend this particular one called Melatonin in Mitochondria, Mitigating Clear and Present Dangers. It comes from a Dr. Russell Ryder and others. And he's been a long time melatonin researcher, particularly mitochondrial melatonin. So let's go through this. I'm going to go through this particular slide through a series of slides here as we sort of build on this information. Okay, so glucose gets transported into the cells through our GLUT transporter mechanism. And then that glucose will go through glycolysis, as we just discussed, to form pyruvate. Now, pyruvate will move. This is in normal oxidative phosphorylation reactions. So pyruvate will move into the mitochondria. So now we're inside the matrix of the mitochondria. And pyruvate will get converted to acetyl coenzyme A through the actions of an enzyme called pyruvate dehydrogenase complex. And I've done lectures on pyruvate dehydrogenase complex before. One of the critical nutrients for pyruvate dehydrogenase activity is thiamine, for example. Now, notice that acetyl coenzyme A, okay, can enter the citric acid cycle. So we've already gone through that, and then that segues over to oxidative phosphorylation. Okay, so we get that the major effect at the electron transport chain level for ATP production. Notice also that acetyl coenzyme A is used as one of the main cofactors for the conversion of 5-hydroxytryptamine to get converted to NAS. NAS is N-acetylcysteine. MEL is melatonin. Okay, I'll come back to that shortly. Oh, by the way, one other thing to point out. Right here is something called PDK, pyruvate dehydrogenase kinase. There is a relationship between pyruvate dehydrogenase complex and pyruvate dehydrogenase kinase. Notice that the kinase puts the brakes on the pyruvate dehydrogenase complex. So it's really in depth when you start looking at this from a biochemical standpoint, but there's a lot of what they call metabolic flexibility in the system. It makes sense when you dive into this a little bit deeper. It's just important to understand right now that the ability to convert pyruvic acid into acetyl coenzyme A to initiate activity within the Krebs cycle, we have to have our pyruvate dehydrogenase active. And so it can fluctuate back and forth between an active and inactive state depending on the actions of pyruvate dehydrogenase kinase. So you could think of the kinase pyruvate dehydrogenase as a brake on pyruvate dehydrogenase complex. And there's many things that initiate the brake or release the brake. So if we have plenty of ATP in our cells, or we've got plenty of NADH, or we have plenty of acetyl coenzyme A, those can activate the pyruvate dehydrogenase kinase to essentially break or slow down the actions of the pyruvate dehydrogenase complex. Pyruvate itself, or calcium, essentially inhibits the kinase. So we actually get increased activity of the pyruvate dehydrogenase complex activities, which would make sense. Basically what's saying up here is that if we already have enough energy substrates, we already have enough ATP at the mitochondrial level that's being produced, we don't necessarily need to keep shoving more pyruvate down into the citric acid cycle. So there's a brake and an accelerator that occurs in this particular system moment to moment, okay, every single day of our lives. So the pyruvate dehydrogenase complex, which converts pyruvate to acetyl coenzyme A, is regulated by a number of things. It's regulated by acetyl coenzyme A, it's regulated by ATP, it's regulated by NADH, for example. And so again, if we have enough energy in the system, that reaction will slow down.